Okay. Hello, everyone, and thanks for coming for my talk. It's really a pleasure for me because it's the very first time that I am here as speaker at the conference, Fox Days. Yeah, my name is Marcus Kett, and I'm going to talk a little bit about the Java Cloud Native stack for microservices and serverless architecture. And these are not only the buzzwords, because I use the buzzwords because mostly they confuse me. And when I talk to developers, most developers are also confused. And this was the idea to create a talk about all of these modern buzzwords and giving you an overview what's behind these buzzwords. And with the cloud and cloud computing, everything changes completely. And for a long time, it was not that clear how Java would fit and work in the cloud, if Java is still fast enough and suited for cloud computing. There were so many other programming languages coming up, and it seems for some time that other programming languages can overtake Java because it seems they're more suited for the cloud. But no worries. Java is great, and the Java community redesigned the entire Java stack, and now Java is perfect for executing software in the cloud, and we believe Java is the best programming language to build cloud-native applications for the cloud. And this is very important because there are so many new software applications coming up. You see that video with AI, machine learning, and revolutionary new software for IoT. And so Java is really the perfect language to build all of these new systems. My technical background is I'm CEO of MicroStream. We are contributed to several open source projects. And for me, everything started around 20 years ago with developing a Java IDE called RapidClips. It's still available. It's free. You can download it. And we have been working on a kind of like Visual Studio for Java. This was our initial idea. And we were able to build a beautiful graphical user interface builder, very able to drag and drop modern UIs very easily. But as soon as we wanted to connect these user interfaces with the databases, then we were in trouble. So this suddenly everything became really complicated. And the visual developers, they hate complication database programming. So we worked on improving and simplifying the JBoss Hibernate tools for Eclipse for more than 7 years. We designed a new import for Hibernate, so we can seamlessly import database tables, and it creates the entity classes without any errors, no mappings, so everything automatically. Then we built a new query language because our community was not able to use the common query languages like JPQL or Criteria API. So we created a kind like SQL editor. It created the Java criteria code, which creates through the runtime SQL, so really crazy, but to simplify database programming with Java. And then we were not really satisfied with our solution. We thought they must be even more simple to build database applications, and then we created MicroStream, and 2019 we created a company behind the project. We open sourced it, and now MicroStream is part of Project Helidon, which is a popular microservice framework. We're working close together with the Helidon team, and now it's also integrated with Micronaut. So the Micronaut team, they wrote a beautiful integration with MicroStream, and we're working together now also with the other microservice runtime vendors. to create beautiful integrations. That's something about my background. Yeah, why do we need best possible performance? Yeah, it's because we want to build new innovations. We want to have a better user experience. Of course, saving resources. This is a big topic for the decision makers. Higher productivity. These are all reasons why we need best possible performance. And an interesting study from Amazon, they found out that 100 milliseconds of latency costs them 1% in sales. That's really incredible. So we need best possible performance. And as I mentioned, the cloud changed everything. And of course, this influences us as Java developers. Everything started from the conventional data centers. We had physical servers, and so everybody built up its own data center, run its own data center, every company, and this was expensive. They were not effective in terms of using the infrastructure power. They were expensive, and so on. And then with cloud, everything changed because now the idea is to have a data center or data center resources, infrastructure resources in the cloud, which means this should be available on demand. Creating the cloud resources by infrastructure as a service, like you can write code that creates and prepares the cloud infrastructure you need. So this is really incredible. And also it enabled to build software applications that are available as a service, and introducing the pay-as-you-go model, so only paying for the resources you really need. And these are all these ideas behind cloud of computing. To enable this, some revolutionary changes were, so we need some changes here, and one of the most important game changer was virtualization, of course. With virtualization, we were able to share the resources from physical servers, providing virtual machines. This was already a big step. And then from virtual servers with containers was the next abstraction level. And the containers also changed almost everything. Now we have containers where we can run our software in containers and share the resources under the hood. And then another revolution came up, microservices. What are actually microservices? Before microservices, we were used to write monolithic applications, and the entire Java stack, of course, was built for creating monolithic applications. But with microservices, now we cut this one piece of software into numbers of small modules, small services, running completely independent from each other, being containerized. They run in its own container, in its own infrastructure. And the question on a cloud platform, on a container platform, of course, and the big question was, is the traditional Java stack suited for that kind of software? And of course, this is the reason why I made this talk. It's not suited, because all of these containerized microservices, there are some rules, and called the 12-factor apps, for instance, and there are some rules. So each microservice should be responsible for one specific task. Being small as possible, being able to scale horizontally, run its own container, and if it crashes, it should be able to restart instantly. So startup time is super important. And of course, it should run in small machine instances. I call it micro machine instances. There should be low memory consumption. And also, each microservice should actually have its own database. So these are completely new requirements to our applications, to our services. As I mentioned, there are some challenges with the traditional Java stack because let's have a look on the application servers. Before microservices, we were used to run the monolithic Java applications on big machines on one server, and we had an application server, and we run multiple applications within one application server. So many applications, or as many apps as possible, shared this application server resources. And of course, startup time was not really important because you run this monolithic application once, so you start it once and it runs for actually ever. It had, of course, higher memory consumption and it feels heavy-wide, but it was built for the monolithic applications. And now the question was, should each microservice really run in its own application server? And the answer is no, of course, because there are some challenges with the application server. They are not suited, they are heavy-wide, memory consumption is high, startup time is low. So we need something different for microservices. And the same with the traditional JVM. So the JVM was built running monolithic applications, and we have this great JIT compiler. So all of these people, they have doubts in terms of Java. They say, Java is known as slow, it's memory hungry, and so on. And it's not slow. Because of our fantastic JIT compiler, it's super fast. The problem is that warming up the JIT compiler takes minutes or half an hour, sometimes depending on your application. This is not great for microservice. They should start instantly and should be available instantly. So the warm-up time of the JIT compiler is not that great for us. And of course, the memory consumption is higher through this warm-up time. As soon as the JVM is hot, then it's super fast. Then it's as fast as a C program, I would say, almost. Because of this great optimization of the JIT compiler. But for microservices and to have a faster startup time, the traditional JVM actually is not suited. What's about persistence? Is traditional persistence, traditional persistence, what's that? We were used to use relational databases, of course. We are used to use Hibernate or similar object relational mapping frameworks to be able to store our objects because we want to store objects, nothing else. So this is an abstraction layer. So, and there is a rule that each microservice should have its own storage. So do you want to set up a database specifically for each microservice, maintain it? It's perhaps not that great. Then every microservice should be responsible for a specific task, and which means if you have a microservice that is responsible for storing machine data, perhaps a relational database is not that best idea. Perhaps you should use a time series database. Then you have perhaps you have services that are responsible for complex data. Time series database not really suited for complex data, so we are used to use a relational database, or now the graph databases are coming up. They are fantastic for complex data structure, which means you should have actually multiple databases in your application. So multiple databases means you have multiple effort, multiple costs. And this is the reason why database vendors currently working on multi-model databases, to have only one database and being able to provide you all the different data structure you need. If you don't use a kind of like multi-model database, you have to deal perhaps with multiple database systems. You need the know-how for that, and it's very effortful. So the question is traditional Java persistence suited for microservices? From application servers to micro runtimes, I mentioned already that we saw the further development from application servers to micro runtimes. What does this mean? We have a kind of like small application server, and this was what I have not understood some years ago, honestly. So what are these micro runtimes? It's kind of like application server built for running only one single microservice and providing everything that is needed for your microservice. And from application servers to micro runtimes, and there are many of these microservice frameworks. Here is a big picture. So we started, we have this landscape, Java Enterprise and Spring. It's well known. And then with Java Enterprise, we have these application servers, well known, WebLogic, WebSphere, Tommy, Payara, and so on. Whitefly, very famous. And now we have these new runtimes for microservices, and there are also two categories of these microservice runtimes. We have these microprofile runtimes. Microprofile is similar to Java Enterprise or Jakarta EE, is a standard for microservice frameworks, and we have kind of like microprofile compatible frameworks like OpenLiberty, Payara, Quarkus. They follow the microprofile standard. Helidon is a special framework because it's one framework, two frameworks in one. So they have a framework that is compatible with microprofile, and then they have Helidon SE, which is a more lightweight framework. And then we have all these frameworks that do not follow the microprofile standard, like Helidon SE, Micronaut, and so on. And of course, we have this, the Spring universe. Who is using Spring? Oh, okay. Why are you laughing? Okay. So, which means I can skip this slide. Understand. From JVM to native images, with GraalVM everything changed completely, because now with GraalVM we are able doing polyglot programming, but who is using polyglot programming with GraalVM, by the way? No one? Okay. This is also my experience. So it seems GraalVM is more interesting for creating that native images. Who is using GraalVM native images already? Okay, not that much. How do you create your microservices? So with GraalVM native images, we have revolutionary changes in startup time. They are up to, that's numbers from Oracle, 50x faster startup time in milliseconds. That's great. And smaller memory footprint, perfect. And this actually, I think this was the game changer for Java in the cloud, creating native images. And if you use Spring, then Spring also has an integration for GraalVM, so which means you use it under the hood automatically. And it's the same with Quarkus. Who uses Quarkus? Okay, so they have also a great integration for GraalVM native images and also Micronaut. And by the way, of course, MicroStream has also support for Spring Boot. That was very important to mention. But there are also limitations with the GraalVM native images, and because there are so many concepts, Java concepts, that do not really work great with native images, reflection, and so on. And ahead of time compiling, it takes too much time, and it's really mostly linked to additional effort to run GraalVM native images on different infrastructure. So, and I see on conferences that not much people use it. So I'm wondering if there's whether it's there a better solution or not. And I guess what is also now a great change is OpenJDK project Krug. This enables to create snapshots of your warmed up JVM. So your JVM optimizes everything and it's hot, and then it gets stored. So the state of your JVM gets stored persistently on disk. And if your service crashes and starts again, then the JVM loads the latest stage of its warmed up JIT compiler, and it's there instantly. Then the warm-up time is much shorter, and we have great numbers. So you can, and the advantage is you can keep your JVM, we can use all Java concepts as we are used to, and we have super fast startup time with this project Krug approach. Azul is driving this forward with Azul Ready Now. The Open Liberty team has integrated it with OpenJ9 Instant On, and AWS has introduced Corretto Snap Start that supports that functional principle. So you get it out of the box. That's really great news. And it depends on the use case. We have now GraalVM native images. We have Project Krug that is supported by the JVMs, and you can choose, and that's always great. What we have in the Java community, that we have different solutions and we can choose which one is better suited for our use case. Serverless computing. How does this does all of these work with serverless architecture? And serverless, by the way, in my perspective, in my opinion, this is the next level of abstraction. So, which means I want to build microservices, and I want to run microservices, but I don't want to have this DevOps effort managing Kubernetes cluster, and so this is mostly very effortful, and so the idea is that you only have a container, you deploy your app and run this app in this container, and everything is managed by the container platform. This is the concept of serverless architecture. You don't care for anything, super easy to use, no DevOps, almost no DevOps effort, and everything is managed by the cloud provider, by the cloud infrastructure. And for instance, AWS Lambda, serverless functions. And the cool thing is that you can run almost all Java programs seamlessly in a serverless function. So, my friend Anna Bean has introduced how you can even run monolithic Java apps in a Lambda. So this also works. So you can reuse your existing applications and migrate it very easily to serverless computing platforms like AWS Lambda. There we have, the idea is we have smaller machine instances, so you can have smaller machine instances, smaller than one CPU, so you have micro CPUs, micro cores, and smaller than 1 GB memory. It works from 512 megabyte of memory. And the great thing is you pay only for what you really use. If you run a Kubernetes cluster, then you have the common cost for only running the Kubernetes cluster, even if it does nothing. If you have serverless functions, you can have millions of serverless functions, and they cost you nothing if they don't do anything. And that's really great because we have so many applications, or most of business applications I saw in the past. There are only some modules that are really used all the time, and there's so many other modules of these applications. They do nothing. They are there. You have to maintain it all the time, and increases your need of computing power in a data center, but actually they do nothing. And with serverless functions, you can implement everything, run or provide everything. If it's not used, then you don't pay anything for that. That's cool, but on the other hand, there are also challenges with serverless functions, of course, and it depends on the use case. If you have so many services that are not really used, then perhaps the serverless approach is better and cheaper for you. If you have services that are used all the time, perhaps then serverless functions are more expensive in comparison to a Kubernetes cluster. So check it out if this works for you and is suited for your use case. Persistence. Do we actually need a specific persistence for microservices? What's the problem actually with persistence? So we are used to use relational databases, of course, and to be able to store objects in a database, we have learned this not really works seamlessly, because in Java everything is an object, and it's not possible to store objects in a relational database. So, and also the data types, like PostgreSQL supports around 30 or 40 data types. How want you want to use these data types in Java? So there are so many mismatches. It's known as impedance mismatch. And then the question is, are the NoSQL databases perhaps the better approach? Who uses relational databases, by the way? Of course. NoSQL databases? Okay. MongoDB? Neo4j? Okay. So the question is, are they better than relational databases? And we discussed this on so many conferences. It depends, I would say. So they are different, of course. They introduce completely new data structure. I think this is the most important changes. The data structure change. Now you don't have to deal with tables. You have now JSON or XML or column stores, graph. There are also object-oriented databases that were introduced in the 1990s, but didn't work very great. So I guess nobody uses object-oriented databases anymore. But we have the same or similar impedance mismatches, because if you have a very complex object model with circular references, for instance, it's not possible to use JSON for that. So, of course, it depends on the use case, what is suited for you. To solve this problem, which means the problem I want to store objects, so I want to have persistence for my objects, and it's not possible with relational databases, so I need an abstraction that cares for that. And we are used to use object relational mapping, great concept, so we worked on that 5-7 years. And everything, okay, that works with relational databases. But there are, of course, some trade-offs. And it's because you need that mapping through runtime, through every single read and write. And this slows down your queries. So Hibernate, for instance, has to generate objects under the hood all the time. So even if you read data directly from a cache, you have these delays. So, and you need more computing power, of course, because object relational mapping is an expensive process behind the scenes. So you need more CPU power, which means you need bigger machines, and your costs will be higher. But we are used to use it, of course. That's standard. So you can read all about this everywhere, impedance mismatch. And we have seen that if you use Hibernate, for instance, as an object relational mapping framework, the performance goes down. It's not that great. So by the way, if you can make comments all the time, correct me if I tell you nonsense. We saw that performance goes down, so how can we improve that? Of course, we use a cache. And it's standard to use a cache, but you can see now the infrastructure gets more and more complex. and there are additional source of errors in terms of cache configurations. So complexity increases, but of course the performance is better. So then let's have a look on distributed applications. Who of you creates distributed applications? No one? Okay, interesting. So if you have a distributed application, which means you have an application node that runs multiple times in parallel to handle the workloads, then you need additional instances of your machine, and the cache stores all the data, the queries locally. Now you change, let's say one of these node changes data, stores the data into the database, then this application node and the database are in sync. But the problem is all of the other application nodes are not in sync with the database. So you have legacy data in your cache. You can now define timeouts, so there are concepts for that, of course. But what we can do and what we see in practice is it's a good idea to put the cache between the application and the database. And then it would be a single point of failure, so we need a cache cluster, for instance. Just like Redis, or there are so many solutions out there. You can use JBoss Data Grid, something like that. So now we are able to manage these cache updates, and if the load goes up, perhaps you have to you need a database cluster as well. So you replicate your database, being able to manage higher loads. This is standard. This is a standard architecture, and we are used to use this. Okay, in-memory data processing, why should you use a cache? I think this is pretty clear. It's because of the performance. So reading from cache can be 1000x faster than reading from disk. This is standard, and we were wondering, is there a better solution, even a better solution that is more simple, and can it be much faster? So should we build the next database? So on DB Engines, you can see there are 350 databases. So should we develop the next database for the cloud? Perhaps not. That's not that interesting. There are so many databases existing. So what we want to do is, can we use the Java concepts for persisting? Because Java provides almost everything. You have this, it's super fast, you have this just-in-time compiling, so the JVM is great. We have GraalVM native images, so the apps are fast. And by the way, which means everything we execute in memory will be super fast because of the native image or the JIT compiler, which means if we are able to process data in memory, it will be super fast. So the question is, can we use this performance of Java for data processing? What about the data structure? Should we invent the next data structure? Perhaps not, because Java provides a great data structure. You have objects, you have object graphs, and the object graph is the best data structure we have. All the databases have data structures, they are limited. With an object graph in Java, you can use everything. So it's from nature a multi-model data structure, because you can store time series data. You can of course, build high complexity in your object graph. You can use all Java types. You can use collections. You can use JSON within and store it within in memory in your object graph. That's great. So why not using Java object graphs? We do it anyway. What's about searching? Have you ever used the Stream API, Java Streams? Yes, great, of course. Is it slow? Sometimes. It depends. Best answer always, it depends. it's super fast. Check it out. Build an object graph, run with, let's say, 74 gigabyte memory, super complex object model, and search it with streams. Great results. You have microsecond query time. And by the way, this is also a reason why we call it microstreams. Because micro query time, and in comparison to a JPA query, searching streams with streams is 1000x faster than a comparable JPA query. Tell this your customer. Okay. Not that great, obviously. But I believe it's super great. So all queries are around 1000x faster. And then we have, of course, we need storage. We need persistence for your object. Now, everything we do in Java in memory is fast, of course, but we have to persist data. The cloud providers, they introduce now the cloud blob storages, like S3, Amazon. What is a blob store? It's a binary store. It's built for storing binaries. And most users use it for storing pictures or any files. But the question is, can we also persist our objects in cloud blob stores? Why should we do that? Who of you uses database as a service, like Postgre as a service? Okay, so this is not that cheap, right? In comparison with setting up PostgreSQL on your own server, running on your own server. In comparison, yeah, it's because you have to pay the machine. Perhaps you need a replica, and it depends on the size of your machine, how expensive PostgreSQL as a service is. In comparison to blob stores, it's incredible. Blob stores are incredibly cheaper. 99% cheaper. For instance, if you run a PostgreSQL as a service on an 8 CPU machine with 16 gigabyte memory, you will pay around $4,000 per year for this database server. 250 gigabyte of data. That's not that much. If you buy 250 gigabyte blob storage, you pay $70 per year. That's incredible. So the question is, how can we use cloud native storage for our applications? And there is a concept already existing, and many Java developers had the same idea. The functional principle is called system prevalence. You can read it on Wikipedia, of course. And the concept is actually simple and is very similar to the project Crack, what the JVM now does with the state of the JVM. So just create a snapshot of your state and restore the snapshot. You can do the same with data. The concept is keep your objects in memory, execute your object or execute your queries in memory. Then you have fantastic speed. It's unbeatable. And if you need persistence, just create a snapshot. The functional principle is known then more than 15 years, perhaps even longer. The question is, why is this concept not used in practice? Perhaps because there are so many trade-offs. You cannot create an entire snapshot of your entire database all the time. And something changes, you have to store your entire database. If the application starts again, you have to load your entire database into the memory. But this is crap, man. You cannot use this. But imagine if you are able to create only snapshots of your changes, then this concept is a game changer. And actually, this is what MicroStream does. And I'm very proud to now tell a little bit about MicroStream in 4 minutes. Because it's not only open source, we have now changed the Eclipse Foundation. We are preparing to push the entire code to the Eclipse Foundation and it become an Eclipse project in 1 or 2 months. This is a kind of like definition. MicroStream is a Java native micro-persistence buzzword. Java micro-persistence layer that runs within your application or microservice, similar to Hibernate, and enables you to store any Java object graph, any complexity, any size, persistently into any data storage. And it's recommended, of course, to use a blob store because we just serialize the objects into the cloud stores. You can use also plain files, but then you have to manage your persistence for your own. If you use a cloud blob store, everything is managed, fully managed out of the box. You can restore your object references anytime, and you can restore only what's needed. So you don't have to load your entire database into the memory to process data. You just use lazy loading, and then you can load subgraphs on demand and execute and load only data that are really needed into the memory and execute and search with Streams API. This is actually what MicroStream does because this is the only thing missing in Java. There is no way to store object graphs seamlessly and restore it in memory when needed. You can see the code on GitHub, of course. You can join our development, 2 minutes. You can download via Maven. It's integrated with Micronaut and Helidon already, I mentioned it. And it's super easy to use because what we have done is when we have a look on the database side, we have a database server, a traditional database server. And when you have a look internally inside the database, you can see there is a database management system. There is storage, of course. There is memory. And of course, a database should have a lot of memory to cache queries. Then on the Java side, we have Hibernate, for instance, a local cache. And what we have done with MicroStream, we replace object relational mapping with just serialization with MicroStream. We keep the data in memory, which means it's in memory already. So your data become in memory, kind of like in-memory database, Java native in-memory database. And it's because it's already in memory, we don't need memory on the server on the persistence side, so we can eliminate that. The only thing we need on the persistence side is the storage. And then the architecture gets very simple, and we don't need a cache anymore because our data are already in memory, so we can eliminate also the cache local. It's the functional principle, and you can run it with everywhere where Java runs. You can use it with JVM languages. This is the complete stack of MicroStream. It manages if your classes change. It has a storage garbage collector that cleans up your storage all the time. So all of these concepts are included with MicroStream. That's completely open source. On our website, you can check out the performance demo. That it's really true that all queries are around 1000x faster. And if you run MicroStream in a cluster, then magic happens. So this is the traditional cluster architecture. Give me 1 minute, please. Replace the machine instances of MicroStream, then you can save lots of CPU power. You can save lots of machine power. We don't need a database cluster anymore because we have binary storage like AWS. It's already clustered, it's high available, and so on. So we can eliminate a database cluster. We just need a binary store. Because of everything is already in memory, we don't need a distributed cache anymore, can be eliminated. Then you have a plain architecture, and this is great for microservices, to scale microservices and run microservices in a distributed environment. And there are so many advantages, and everything is provided as open source. And you can also run it as a cloud service in some weeks. So I go to the conclusion to be ready to finish in time. This is only marketing. So one of our customers, like Allianz in Germany, they save up to 90% infrastructure costs. This is only one example. And I want to go to the conclusion. So from monolithic applications, we have great changes and to microservice infrastructure and serverless architecture using micro runtimes or Spring Boot, of course, with GraalVM native image support or modern JVM supporting Project Crack. You can keep Hibernate and use relational database, of course. You can use everything you like. You can use MicroStream as an Eclipse project soon. And so we have great stack. This is the new stack for cloud-native Java applications in the cloud. Check it out and send me your comments. Thanks for having me. It was a pleasure to speak here at the Fox Days, and have a great day. Thank you.